Good morning, everybody. This is Group 8's presentation on why a long hull is faster than a short hull on a sailboat, or I guess just a boat in general. So the observation that got us thinking was we found the boat pictured up here. I will be writing on the screen a little bit. I apologize if I'm not near as good as the professor. So anyway, we found this boat pictured here, which is called the Vestas 2, and it holds the world record for the nautical mile in sailing because it is the only sailboat that achieves speeds of 75 miles an hour or roughly 65 knots. So from this, we asked, why does the sailboat have to be so long? Why can't it just be shorter and simpler? So after a little bit of digging, we determined the hypothesis of the longer the waterline, the faster the sailboat, or just, I guess, boat in general once again. So we need to define our waterline. Now our waterline is determined as the furthermost point forward and the furthermost point back that are submerged in the water. Now if we measured the overall length of the boat, which would be from bow to stern, it would throw off our numbers, in some cases quite significantly. So now we need to look at, how does the waterline affect the speed of the boat? Well, a little background here. As the hull moves through the water, it acts as a piston, and it pushes a wave of water up at the bow. The bow wave crest forms a short distance in front of the boat. Now when a boat reaches its hull speed, which we'll get to in a second, it gets trapped between its bow and stern crests. Regardless of the power applied with the sails or engine, it cannot climb this bow wave. So if you reach your hull speed and you apply more power, you're only going to change the angle of the boat, not its velocity. So to do this calculation, we start with the Froude number. And just a refresher, the Froude number is used to determine the resistance of a partially submerged object moving through the water. And the V is the characteristic velocity of the boat in this instance, and the C is the characteristic velocity of the water wave it creates as it moves through the water. Now, through some derivation using the Froude number, the speed to length ratio is calculated. And once we have this derived and calculated, in most practical cases, the speed to length ratio will be 1.34. Now our whole speed formula, shown here, is equal to 1.34, which is the speed length ratio, times the square root of the length of the water line. And from this basic formula, we can clearly see that the larger the water line, the faster the hull speed. Again, or boat's maximum speed. And just a little fun fact on the matter, a happy balance between speed and fuel consumption would be just under the hull speed. So if you're traveling just under your hull speed, you're maxing your fuel economy as well. So some conclusions on the matter are that the longer the hull, the faster the speed obtainable due to the longer waterline it creates. Now, given the basic physics motion formula, the velocity of a wave is equal to its wavelength times its frequency. If we keep the frequency constant and increase the wavelength, the velocity must increase to pass the larger distance in the same time. So, therefore, the longer the wavelength created by the longer water line allows for a larger or faster velocity for a longer boat. Thank you, guys.